So it's my pleasure to introduce Greg Waller today. He received his BS degree in meteorology from Texas A&M in 1992. So after working for a private firm in Houston for 2 years, performing mostly marine and tropical forecasting, he joined the National Water Service in 1994, working in operational meteorology at the National Weather Service office in Columbus, Georgia, Houston, Galveston, San Angelo, Texas. In 2000, he transferred to the West Gulf River Forecast Center, where he has served the last 23 years, first as hydrologist, then senior hydrometeorological analysis and support forecast, and finally as service coordination hydrologist. His duties are to serve as liaison and lead the coordination effort for the RFC into the future. Please welcome Greg Waller today.
All right. Excellent. Thank you very much. Yeah, I was asked, please, would you consider giving a seminar? And I jumped in and I went, oh, heck yeah, I'm going to do this. It's always an opportunity. I have to engage multiple crowds. And one of the things that I don't get an opportunity very much in the DFW area is engaging the university crowd. We have strong relationship with the University of Texas Arlington and their engineering firm or their engineering departments. But TCU is kind of more of a liberal arts school. We do get down to Tarleton and Stephenville, but and North Texas has an emergency management. But there are so many universities across the state of Texas, and when they said, will you come give a seminar, I almost didn't let them finish the sentence. Yes was already out. What I'm going to do is I'm going to talk about what we do at the River Forecast Center, and it's tip of the iceberg, the 10% above that you see. I'm going to hit that 10% marks. There's a lot that goes on underneath where we dive into the specialist. A lot of specialties, a lot of scientists. Hydrology is a blend and a mixture. I know that the engineers don't like hearing that, but I mean, it starts with meteorology, and Mother Nature is undefeated. You can try to guess what's going to be her next step, but there's so much that goes into the science. So we're constantly learning. I'm going to do some introduction of products, introduction of who we are as a federal government agency. There's always going to be time for questions and answers. I know that we've got a pretty good crowd here in-house and a crowd online with the Zoom. I'll do my best to answer all the questions. And if for some reason we run out of time, my email information is going to be available, and y'all can email me at any time. I'll answer these questions as we go. I want to start out in the Weather Service and in the government in general. There's a lot of paperwork and a lot of bureaucracy. To find the National Weather Service, first you start with the Department of Commerce. And then under the Department of Commerce is the National Oceanic and Atmospheric Administration. This one's kind of common. A lot of people recognize NOAA, the Marine Fisheries Service, the National Ocean Service. But we're kind of proud of our logo, the National Weather Service. We're three logos down, but we are the agency responsible for pretty much all the day-to-day activities and all of the weather and water critical elements that would possibly cause you to suffer loss of life, loss of property. In that, how we do that is in the weather world, there are 122 weather forecast offices across the nation. They're smaller, 45, 46 counties in the state of Texas. They handle a large component of the weather. The 13 river forecast centers, it's rainfall or precipitation. Once it hits the ground, what happens to it, and how high the river is going to get, and how fast are they going to respond. What is one of the more critical areas, though, is that one that says 21 center weather units. They're at the large airports, Intercontinental, DFW, Albuquerque, Memphis, and they assist the FAA with getting transportation across. I mean, if you ever look at the number of planes over the United States at any given time and how critical the weather is, that might be one of the most undersung, and underappreciated units in the Weather Service would be our center weather service units. But there's 21 of those spread out across the nation as well. This is a busy slide, and I put a lot of logos on it. I own almost none of the data that we work with. It is a partnership between federal, state, local, quasi state level, university level components. But the goal, let's get all the weather, the water, and climate information. And that means observations, forecasts, and warnings for all of those elements. Provide them to the public. so that the public can then make the decision, what can I do to save life and property? That is a change in philosophy from when I started. And it was you gather the data and you put it out in the best forecast possible, and you're done. But what we've learned is if you issue a forecast and it is in a way that the user does not understand it, and most of the time I'm going to say public, I can use a vocabulary for engineers and I can use a vocabulary for meteorologists, but the public, this isn't their expertise. We have to find a way to get this information so that they can make an informed decision. So that is the key. If the public does not understand the forecast has no value. So we've got to create that step, and that's the new paradigm of the National Weather Service. The river forecast centers, we look funky, and it's because we follow Mother Nature. If a raindrop hits the ground, where does it drain to? You know, the continental divide, the river system and river basins. We do not, it really doesn't matter a geopolitical boundary, a county, a state, it doesn't matter. It's the river basin. So we have 13 river forecast centers across the way there. And you're looking saying, whoa, 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 Greg, I'm only seeing 12. It's because there's one in Alaska to cover that region by itself, the Alaska Pacific region. And it is such a large footprint. I mean, it'd be like the 7th or 8th largest country on its own when you count its size, because not only do they do that, but they have responsibility for any hydrology that would be occurring in Hawaii or any of the local flood issues in some of the Pacific Islands as well. We predict rain. That's the difference between the weather forecast office and us. The weather forecast office, when you got up this morning, you said, do I need a jacket or so? Let's see what the forecast is. Oh, it's clear. It's going to get breezy today. Lows in the 50s. Highs, man, we're going to see 80s today. That all came from a weather forecast office. None of that comes from us because we are rainfall or precipitation forecasters. That allows us to have a bigger footprint. I don't care if the wind's south, southwest, or southwest. I don't care if it's 98 or 99 or 100. It's all hot. What we care about are the parameters that it takes to create precipitation. What phase is that precipitation going to be? I don't like snow. Snow is a 4-letter word that begins with S, but we have a small snow melt component in the upper Rio Grande. If you look, it kind of looks like a chicken facing to the west. You know, we call that the chicken head, but there's a snow component. But if it's going to be rain, what are the parameters? Is it a nice stratiform drizzly rain? Or is it a convective heavy rain event like we saw Monday night where we have 17 inches of rainfall in about 6 hours? What is the rainfall parameters? When it hits the ground, what's going to happen? How fast is that river going to respond? So then we zone into land use, topography, soil types, and we try to estimate the volume of water moving downstream. So there's always some science that you can choose to try to make a little bit better. I mean, I've already mentioned meteorology, knowledge of geology and geography, geology for the soil types, just geography, just because someone's going to say, hey, I'm at Village Creek at Koontz and there's water over the road here. Well, you better know where Koontz is, which is Southeast Texas, and then where is Village Creek in that? So you've got to know the geography, the meteorology, the hydrology, the geology, and all of the above. So that's why I say we really want a wide variety of sciences in our office. This is my area of responsibility, 400,000 square miles. Texans suffer from Texas hubris. We are not the biggest. We're not the baddest. I mentioned Alaska is #1. Even in the continental United States, the Missouri Basin River Forecast Center would be the largest in the continental United States. The argument among hydrologists is technically they say the Missouri River is the longest river in the United States. And I would argue the Missouri is a trib of the Mississippi. So therefore you got to add it, and it's the Mississippi because the trib by itself, if you include the whole river. I know that's argument and that's nerd talk, but the point is it's big. They go from Kansas City to Montana. Our area goes from the Texas-Louisiana border to the international border, and there it gets interesting. The international border, you have to start defining between the two countries' responsibilities. Our office is responsible for the forecast. The river will get to this height based on this information. Right now, the critical nature is water supply and water accounting. That comes from the International Boundary Water Commission in El Paso. So any decision made from them, they will relay to us. When we see flood events coming, we relay it to them. They are the ones responsible. They are the Department of State. They are responsible for coordinating with our Mexican counterparts. SELA, which is their version of the Department of State, Conagua, which is their science agency for river forecasting, and they have a meteorological service, the National for Meteorologic, that is their meteorology component. trust me, when there's big floods, scientists are talking to scientists, and we let the politicians speak to the politicians, because getting the information to save lives in a timely manner is the most critical piece of information there. If you look up in the upper chicken head, I said snowpack, snow water supply. This is my 24th year here at the River Forecast Center. We've only had 5 above normal snowpacks. Water is critical in southern Colorado, on the Rio Grande for New Mexico and down. And this year is only a little bit above normal. So it is super critical to calculate the volumes of water that are measured in the snowpack, so calculations can be made for the city of Albuquerque and all the agricultural interest. It gets to the international border. There's 87,000 square miles of interior Mexico that a raindrop could fall and feasibly get into our lakes. I think there's 7 lakes on the Rio Conchos alone that would come into Presidio. There's a series of lakes from Del Rio, paralleling from Del Rio to Laredo. There's the international lakes Amistad on Del Rio, Falcon, which I've been at earlier this week, down south of Laredo. And then once it gets down to the lower valley, with the huge influx of people down there, millions, there's a lower project to where they will control the water that goes through the Rio Grande proper by a series of flood waves. Tropical threats, we're going to see tropical activity in the state of Texas. It's going to happen. Well, you're bringing a surge coming up, a saltwater component. We're trying to forecast that. But the main thing is it's bringing a surge of tropical moisture in the way of heavy rain events. If anyone asks, category 3, category 4, category 5, 12 storms, it only takes 1 storm, and it doesn't have to be a hurricane. I fear a weak tropical storm as much as I do a strong hurricane. Allison, Claudette, there's a lot of history-making storms that were just tropical storms that produced critical, catastrophic flooding. So any tropical activity we monitor. If you get up in the Dallas-Fort Worth area, and this is Dr. Gordon Wells with UT's remote sensing group, he's got it in my face. He goes, "Greg, you're wrong." I say there's only 1 natural lake in the state of Texas. It's Caddo Lake, and it's not in my area. And he's like, "There's the Playa Lakes, and there's all those." I go, "Okay, well, there's only 1 natural lake that we would model. It's not in my area. It's this little section up here that's actually in far northeast Texas." Every lake in the state of Texas was built for a reason, most of them in the 1950s in response to that drought. But why was your lake built? What are your operating plans? Because when heavy rain starts coming, we need to coordinate your releases so that my river forecasts look better. So now you've created this geographic footprint of knowing all the major lakes who are Army Corps flood control. We don't like that. Flood mitigation. You don't control flooding. Mother Nature's undefeated. Remember that phrase. Mother Nature's undefeated. You mitigate flooding. You try to minimize it. The water supply reservoirs do not have room. So water supplies fill up. Flood mitigation projects say, "We'll hold, y'all let your water go down." So now you've got a multi-agency coordination, which is where my job really comes in. The city of Dallas alone can have 9 different large reservoirs release water. And I'm expected to hit that forecast 5 days out to a 1/10 of a foot accuracy. So tell me how difficult this job can be with all the coordination. We have the rocky terrain here in the Austin, San Antonio area. It goes all the way up from the Georgetown all the way down through New Braunfels, and they call it flash flood alley because you have steep slopes, rocky soils, fast runoff. You're close enough to get to heavy rain events. So everyone talks about tornado alley as Kansas. Well, we've actually coined the term flash flood alley here for the Central Texas area. You better not wait until you see the rivers respond. You better jump on the rainfall signature to get that river forecast out. And then I joke about this area of the Nueces because I don't know how many forecasts I've missed from groundwater recharge where floods have gone through Asherton and Derby and never made it to Cotulla or Tilden, and I don't know where the water went. So when someone says, "Hey, what's going on in the Nueces?" I just say, I don't know. So anyone that does that, please let me know if you can forecast the Nueces, because I've been there 24 years and I still can't forecast the Nueces. So who am I? You can see I'm outdoorsy. I love my kid. He's an Eagle Scout, but I am the outreach position. I get to travel across this entire state and southern New Mexico, central New Mexico. Haven't been to southern Colorado much for my job, but I go up there to visit as much as I can. Class of 92, yes, I'm getting up there in years. So now it's time for me to start passing, the extraction of knowledge is what the term was used, to our younger staff, because our younger staff, they have a different education paradigm, definitely more plugged into technology. But how do you accomplish the geography, the geology, the hydrology, and the meteorology to a younger group so that when I get to enjoy more outdoorsy stuff, I'll get to to feel safe knowing that I left it in better hands than what was given to me. You heard my career, except for 8 months in Columbus, Georgia, I've been in Texas. Raised in Texas, high school in Texas, college in Texas, and worked in Texas. And I'm still learning Texas weather and Texas hydrology even to this day. And for those that ask, even though I've been in the Dallas-Fort Worth area for 24 years, all of my sports allegiance remains to Houston and to Texas A&M. I'm sorry if I'm on the wrong campus for that. You can see my son, that was our trip to Guadalupe Peak on the left. And then the us playing paddle guitars, that would be us up in Minnesota on the Boundary Waters. That monument there is, one of us is in Canada and one of us is in the United States at that point. So let's get into what does the West Gulf River Forecast Center do, okay? We're going to use some acronyms. People joke NOAA, the National Organization for the Advancement of Acronyms. I will try to explain all the acronyms that I use. HAS is our meteorology, hydrometeorological analysis and support. We dive into the meteorology. Hydrologic operations would be river forecasting. We do the modeling in-house. So we have to have patience with data and calibration. And then what advances are there? The main advancing is computing technology is allowing us to tie into other models, the HEC-RAS model, from the Army Corps, or, distributed modeling or whatever. And then the big one is GIS applications. So now we're really tying into that geography component with GIS applications. We deal with the water cycle, okay? Specifically, all of this from the evaporation, we monitor the meteorology, then when it moves into areas, when it hits the rain, then once the rain falls, rainfall rates, when it hits the soil, impervious, runoff, timing, to flowing and monitoring that as it moves downstream back into the Gulf and the hydrologic cycle. We do not handle groundwater. So Edwards Aquifer Authority and all that, they said, hey, what can you do to help us? And I said, we are not groundwater specialists. If they ask me to groundwater, I will be retiring by the end of the week, because that is a completely different scientific beast that I haven't figured out hydrology and meteorology. Why would I jump into groundwater at this point? I did have a coworker, Phil Baker, say, when Camille listened to one of your talks, she thinks she got it. And I went, yeah. So this is how I do my job from a kindergartner's point of view. And Camille Baker, yes, you nailed the hydrologic cycle. So even a kindergartner can understand what I do for a living. The river forecast process. When I first got there, they really didn't like the rainfall forecast component because the rainfall forecast was so variable. And why does it matter? You can be off as little as 15 miles and miss 2 river forecasts because you said it was going to rain here, and that's a false alarm, but it actually rained over here, and you missed the probability detection. We are handcuffed by the forecasting skill of meteorologists. I will say that in my career, we've advanced from a 0 to 6 hour forecast lead time on QPF, quantitative precipitation forecast, the actual amount in an actual location in an actual time frame. We've advanced from 0 to 6 hours to 24 to 30 hours in 24 years. And you go, man, that doesn't sound like much, but you don't understand. I mean, that's a quadrupling. What happens if in the next 20 years we were able to do that again and we were able to go 4 to 5 days out? Imagine giving 5 days of lead time in the Austin, San Antonio area that you're going to see a heavy rain event and this Onion Creek is going to flood. Because right now we wait until we see a radar signature projected to move in that area, and then try to get 6 hours of lead time on Onion Creek or 12 hours of lead time on Onion Creek. Imagine giving 5 days. That's our goal. We capture the rain on the ground, rain gauge, radar, and satellite. And I've got some slides to explain that. We do the rainfall forecast. We do know we see patterns that's going to rain 5 days from now. How can we, without locking into a forecast, how can we tell you 5 days of forecast now to get you some idea? And that's through ensembles. So we will use weather ensembles to create a series of hydrologic ensembles to give you an idea. The river is going to be somewhere between 28 and 30 feet, and that's critical for you. Most people say 28 to 30 feet. That's not much of a river forecast. We already knew the river is going to get high, but at least ensembles are giving us some skill to extend our lead time. Soil conditions, we run a Sacramento soil moisture accounting model, and it's continuous. So we keep putting rainfall in or no rainfall and it keeps drying out. We're trying to simulate the soil conditions as they are. We factor in those pre-mentioned lake releases so that we issue a series of river forecasts to our weather offices. They look it over and they add impacts. Okay, so I'm not the one issuing the river forecast to the public? It's because there's 254 counties across the state of Texas. We got a huge footprint. I can't know the local impacts. I can't know when a subdivision is built on the river's edge. So we rely on our weather forecast offices to go out and gather the local emergency manager and floodplain manager information so that the river impacts get relayed back to us. And then we know, hey, when the river gets to this high, this bridge is threatened and this subdivision is threatened. We issue the numbers, they issue the product to get the public's attention. We have to watch our vocabulary. Work closely with Harris County Flood Control and Jeff Lindner. Now he put this map up and he said, okay, well, we had a 50,000-year event for Hurricane Harvey. I said, did we have a 50,000-year event? And the answer is, if you look over here, you can see that the rainfall frequency over 4 days was a 20,000-year event, okay? In the same area, though, the hydrologic response was only a 10 to 50-year event. So what event was it? Are you talking about hydrology? Are you talking about rainfall? You talking about, the best one that got me is after the 2016 floods, they interviewed a lady on the west side of Houston. She goes, I don't understand how we can have 300-year events in 2 years. And I said, we have a messaging problem. The 100-year event is not every 100 years. It's a statistical reference. So I told our staff, no more 100-year, 50,000-year, 5-year, 20 years. Don't say that, okay? It's the river to impacts, not the frequency. People are not understanding a rainfall frequency. So in Jeff's case, it was a 20,000-year event and it was a 20-year event in the same spot in Texas and same spot in Harris County for that matter. We do not use return frequencies. We use categorical impacts. Green, river's good. Action stage is, you know what, the river's getting high. We want the river forecast center to start issuing forecasts so the public will understand. Minor flooding, the river is now out of its banks, and just because the river is out of its banks, we do not necessarily call that minor flooding. It's and when it has an impact on humans. You have to close down the city park because you built it in the floodplain by design, and now there's a danger there. Some of these small secondary roads, you're going to have to close. If it keeps rising into moderate, that means significant roads are getting threatened or underwater, and you're starting to threaten buildings in the area. Major, water's in buildings. Water's hitting, primary roads. You see, it's a level of impact. River's out of its bank and a small impact on a park. River is out of its bank, and okay, now we got to redirect some traffic. River out of its bank, and now we got buildings threatened. And then obviously record is it's never been this high before in the period of record. So we try to do a color coding scheme. I tell everyone, if you start seeing our map with reds and purples on it, that's when you need to start acting that this is a significant event. Minor flooding is, maybe you walk the trails, your low waters, some of these low water spots are going to be underwater on minor flooding. I have that problem with the Trinity Trails up in the Dallas-Fort Worth area. Okay, I got to change, some of my patterns here. But moderate or major, humans better be taking, the possibilities of actions to protect from floodwater. Our hydrometeorological analysis support unit, basically, they're our meteorologists. You work a meteorology shift, even if you're an engineer, and the meteorologist can work river forecast shifts. We are all cross-trained, but know that when it hits the fan, experts on their expertise. Our HAZ meteorologists are looking at the weather parameters, rain gauges to see if they're reacting as expected, satellite data, and then we're doing a rainfall forecast. And it's constant over and over again. We're also creating a temperature data set for snowmelt, which is super critical this time of year because our snowpack is starting to melting out, and we got to work on that water. And then it's just data quality control and situational awareness. Hey, did you see it's raining 4 inches an hour? We've got it in a rain gauge over near Coots. Yes, okay, then let's go for it. So with that, there is no one gauge that captures it. We have a program that gathers all the gauges, all the sensors. So a good rain gauge network is superior, but you have to quality control for when they get clogged or when they start misbehaving. The radar gives a great representation of the geographic extent. So the radar is telling me where, the rain gauge is telling me how much. However, you get in sparsely populated areas, you get far away from a radar, you get blocked by a mountain, you fill in with satellite. When I started, satellite data was pretty crude, but with the GOES-R satellite in 2016, it is a pretty darn good product, especially to fill in the gaps. The goal is when you glom together the satellite, radar, and gauge, that product is better than a gauge-only field, it's better than a radar-only field, and it's better than a satellite-only field. So people keep saying, yeah, but the radar, it's the Doppler, and it's the super Doppler, and all that kind of stuff. The radar, one, it starts off, and it's the lowest elevation angle is not 0. It's, anywhere between, 0.3 to 0.5 degrees up, which means the farther you get away from a radar, there's more depth underneath the radar that you're not sampling. So the farther you get away, you can miss some really cool meteorology in there. So we can't trust the radar 100%. Let's put some gauges under it and make it more trustworthy. The other thing is when you get closer, it's a radial component. So the closer in, you can really lose with some pixelation versus you get far away and that degree arc in that area is not the same. So we make it all into a 4-kilometer grid scale. So think about that, 400,000 square miles in a 4-kilometer grid scale every hour of every day, 365 days. That's a lot of data points that our HAZ meteorologists are looking at. So this gives you an example of West Texas. I pulled a Presidio event. You start getting at the end of the El Paso and Midland radars. Del Rio can't quite get over there, but that's the Big Bend, and it's critical, especially during seasons when there's a lot of rafting, a lot of tourists. We have some rain gauges in there, but that's the old 1950s Thiessen polygon looking stuff, and that's not a representative precipitation field. But we know if we glom them together and fill in the satellite, the product on the right is superior, the superior representation than a radar only, a gauge only, or satellite only field. That is the HAZ unit in a nutshell. Create a superior data set, superior information going into a river model will help lead to superior information coming out. So again, we're going to sample it. This gives you an idea. We have overlapping radars, we have multiple rain gauges, and we have a satellite. We're going to know that raindrop, and we're going to calculate that volume on a 4-kilometer scale. Okay, so when you start seeing some of these events like Harvey, I think one of our engineers calculated that Harvey, if you would have spread it out over the state, would have put 2.17 inches of rain across the entire state of Texas, from what just fell there along the coast in Southeast Texas. But it's the best estimate field, QPE, quantitative precipitation estimate, because it's still not 100% real. It's an estimate using satellite, gauge, and radar. So our precipitation forecast, we are getting better. We break that down on a 4-kilometer scale. What we've learned with our weather models is it gathers a good geographic representation, but it does not hit the rainfall maximums in it. So we're not saying there's a 30% chance of showers and thunderstorms. No, we're saying it's going to rain this much here and there. How do I communicate the uncertainty of the rainfall amounts? We do that with ensembles. So every morning we have a briefing and we go through past rainfall, future rainfall, the status of the soils. And this is where our GIS folks really came in. Let's start using data layers. Instead of going to one application for one and one application to another and one application, we are able to create a series of briefing environments so that every morning at 8:30, anyone can step in, walk through, and give past, precip, and future forecast on rainfall, which leads us to past, present, and future forecast on our rivers. So how do you forecast the rivers? Well, one, I say I've got to go visit them. So you can see the one on the left is Taos, New Mexico, Rio Grande. I've been on the Colorado River. This is out actually between Sweetwater and Midland. I think this is the most upstream point on the Guadalupe River that I could find going up. And then this would actually be me visiting Redemal Dam, which is one of the diversion structures down on the Rio Grande below Falcon and below Anzalduas. Our river forecasting operations give us the precipitation inputs. We're going to then see how our model behaves with simulations versus how the river gauges and the river is responding. Once they get above those defined criteria, action stage, minor, moderate, or major, we start issuing forecast points and forecast for them. We issue a series of dailies to help with, maybe it's Border Patrol along the Rio Grande. Guadalupe Blanco helps with environmental control. Some of them are just public information type statements. We issue daily forecast and then all the criteria forecast if the river's getting high. Then you monitor it and you keep updating every 6 hours. When it's not flooding, if it ain't flooding, we ain't working, wrong. You go back and you look how the model performance was. Maybe you have to do recalibration. Maybe you find out the USGS is negotiated to put in a gauge and you got to break this one long basin into 2 skinny basins and let's start working the accuracy of it. So there's always work to be done. Calibration, coordination, scripting, whatever. And how can we bring in the new sciences? So right off the bat, when I first started, it was called the NWS-RFS, National Weather Service River Forecast System. It was Fortran based, which means you have 78 lines of code and on line 32, you're off by 1 space, the whole thing cratered. The new CHIPS pattern that came in 2010 that we've been using is Community Hydrologic Prediction Service. It is Java object oriented. You get it working and you can plug in objects to it, which means we have the ability to plug in a HEC-RAS model if it's given to us from the Army Corps. It gives us more flexibility. This is a hydrologic model. It's math. It is not a hydraulic model to try to simulate physics. So we don't, our lag in Ks, our attenuations are done mathematical. They do not take into account physics or friction, okay? And this is the forecast process. We estimate how much of the rain gets into the river through soil moisture. We estimate the timing. If it rains closer to the gauge, that water's going to get there quicker than if the rain's way up in the basin, we're going to have to wait some time for it to come down. We estimate routing, and we estimate the flow. And this is a big one. People don't understand that, on the rising limb and the falling limb, there could be as much as a 10% difference. And we have to rely on the rating curve of flow versus height. All of our calculations are flow. The public uses height. I was once told there's 30,000 CFS going down the river, and he goes, CFS, that's what, chicken fried steak? I don't know what that means. I said, okay, 28 feet. It goes, well, 28 feet, the bridge goes under. So we have to take all of our flow information and get it into a height information so that decisions can be made. Basically, I tell them if I start mentioning CFS out of habit, think of a basketball. And one of our engineers go, it's too small. I said, it doesn't matter if it's too small. A basketball gets the visual. 30,000 basketballs going across every second at least gives you a visual to work with. Now, that's a lot of estimates, and our hydrologist can modify any of them during a real-time event. And you're expecting me to get to a 5-day forecast to a 10th foot accuracy. Yeah, good luck with that. Our process, we have ways of showing basin average rainfall and basin average runoff. So you can see that a few rainfall peaks will create a prolonged, there's a little bit of runoff and then it slowly drains, and then another runoff and slowly drains. So our runoff components, we can see the timing of the runoff in an individual basin. We use the Sacramento soil moisture accounting model. Think of it as buckets, so to speak, with little holes in them. A bucket gets filled, that's runoff, and the bucket stops raining and that slowly drains in the bottom, creating room. So that's a constant process of us updating the Sacramento soil moisture model. The unit hydrographs give us the idea of how fast is the water locally going to get there. We try to find 5 to 7 representative storms. But rainfall across the entire basin, smooth, which is very hard to do because there's normally little pockets of it, but then say, hey, it seems like of the last 5 events, it takes 24 hours for the peak to hit here. We got a 24-hour peak. Let's try to distribute it a little bit more so we can try to figure out a timing component. In the hill country, it's 6 hours or less. In East Texas, it's 72 hours. So you can see you've got to know your soil use, your soil type, your management, and then the responses for this. Routing is the same way. It takes 7 days for water to get the DFW area to Lake Livingston. It takes another 7 days to get to the coast. And if you don't watch it, it could take 7 days to get that last county. We saw that with the Brazos River in 2015, 2016. To get through Brazoria County, the last county, took 5 days. So, you've got to know your attenuation because the peak is going to slowly flatten out. And you got to know your lag. It's a 24-hour lag. It's a 48-hour lag. All this can be adjusted if we need to on the fly. Why would we do that? The October 98 flood on the Guadalupe was so big and bad, it was knocking out gauges. So we're saying, okay, the rain's going to be there, or the flood wave's going to be there tomorrow, but we're not seeing any data. Well, we found out it stopped going the path, a snaky path. It started going straight down and getting there a day faster. So all of our hydrologists realized for the lower end, the Cuero and the Victorias, we better increase the time or decrease the time frame because we're seeing the water get there faster. So we have the ability to modify all of them. It's all put together in a CHIPS display like this. The red lines would be observations, past observation. This red component here, red line, would be current time. So we look in the past and we see this is routed water coming in. This is what we think the local. We saw a rise, but our model simulation is way up here. My guess would be we've got too much local response. Let's pull the runoff back and get this in line because from here on out, this point on out, it's going to send this purple forecast to the public, the weather office, and more importantly, to the next point downstream for its rainfall runoff and lag calculations. We do this, you got to start at the most upstream point and work all the way down. And then when you get more data, you do it again. This is an iterative process, but this gives you an idea. I'm looking up here, I'm seeing dark blue is rainfall, light blue is runoff. We've got too much runoff. Let's figure out a way to pull this runoff back and let's get this model simulating. Good, next point downstream. So you're solving a series of puzzles as each point moves downstream. I mentioned the rating curve. We couldn't do our job without the U.S. Geologic Survey. Lower Colorado River Authority gets us some rating curves, but it's a height versus flow relationship. And you can see when a big flood goes through a sandy channel, it scours the channel. So they've got to take a new rating curve because now 8 feet is a lot more water with a scoured out channel than 8 feet was before. Really big on the Canyon Dam after it spilled at was it 2002 flooding or the 2007 flooding? You know, it scoured out a large section of channel. So the USGS is constantly getting out there, getting us channel estimates for rating curves, height versus flow. What happens is I try to put all this together. This is my job. I put together a graphic that the public can use on social media, our weather offices can use in their briefings, or the State Operations Center or our river authorities can use. We've got a lot of moderate to major flooding going on. Look at all these reds and purples, and we've got another rain event coming. Sometimes you're telling them the rain event is coming, but there's so much water, it's not going to have much of an effect. Sometimes you're holding their hand, but sometimes it's like there's so much rain coming, it's going to add to it. So we're constantly putting out graphics of river status and rainfall. What are the impacts going to be? I say, so what? It's going to rain. So what? The river's going to get high. So what? The river's going to get high enough that your water plant's threatened. Answer the so what so that you can take your forecast, add value to the customer. We do ensemble modeling. We do past precipitation for longer range. We do hydrologic ensembling. The past precipitation, you know, I'm going to bring it up, global warming, you know, man-made climate change. You know, can you use 50 years of past data and feel that it's representative in an environment that 50 years from now may not be the same? See, we're going to have to find some way of tackling anthropogenic climate change. We do percentages. You know, in the past, if you ran 50 years of data, you'd see this river site get above 10 times. You know, so, but is it going to be 10 times? Do we need to tweak it to 11 or 12? So we do have to factor in ensemble modeling in our future operations for some of this long-term stuff. We do a hydrologic ensembling. The point is we know there's a weather bias, but we also know that there's a river bias. This river point tends to under forecast. And we can calibrate it all we want, but Mother Nature's undefeated. So we found a way to try to incorporate hydrologic biasing with meteorologic biasing to give you more of a range of some of these events. So you can say, hey, this is our best guess. It's going to be moderate, but there's a low end chance it could go to major or approaching record. So we're trying to include a hydrologic ensembling forecast to help get the point across. I call it best guess, reasonable worst case scenario. And those are the two that I would brief off of. So in this case, hey, we've got a lot of rain. And this came from the January event of this year, or the April event earlier this year. I said, there's a lot of rain, but you know, we got a low end chance of some really significant flooding right along the immediate coast. Remember my reds and purples. So let's lose this. I said, everyone's going to see some minor flooding, but you know, there's a low chance, not out of the question, non-zero. There's a low chance it could get really bad along the coast. This is how we're using ensembles to help better prepare emergency managers. We do snow melt and watering. I tell you, snow is a 4-letter word that begins with S. It is very tough, but we try to measure the snowpack and calculate the volume so that New Mexico can prepare for its water usage and meet the treaties, because there's a treaty between the United States and Mexico. Then there's agreements where it was recently went to the Supreme Court between Mexico and Texas. Trust me, water is getting to the point of criticality of there's going to be issues if we don't start addressing the water supply. The other thing to bring up, the state of Texas, well, at one point we were having 1,100 people move to the state every day. None of them were bringing drinking water with them. So it's not just water supply for snow melt, it's water supply for water supply that we're going to have to start really coordinating with. We did have an evolution back in the mid-teens where they opened up the National Water Center in Tuscaloosa, Alabama. It was to bring all the federal partners under one group. Let's create a national water model to help assist. Let's have a second model. In the past, you know, you only had the hydrologic model. The meteorologist like, well, the Euro said this, and the dam said this, and the Hurricane Center said. Hydrologists finally have two models to compare to. So they said, hey, we want you to go and test and tour. And you know that I was not going to allow Tuscaloosa, Alabama and the University of Alabama go without, you know, some Aggie shenanigans going on there. But the point is the national water model calculates 2.7 million hydrologic basins across the nation every hour, at least twice. And then every 6 hours, it adds another 2.7 million. And then once a day, it adds another 2.7 million. So there is a huge calculation component going on at the National Water Center, and we are slowly evolving the accuracy of this. It is a much smaller scale. So some of the smaller creeks and streams that we would not, from a river forecast center, predict, the water model is trying to predict. And there is some skill there. Is it make a life or death decision? No, but you can say, hey, the worst of it's over. Now we can start responding. And we've had to use that both in the Mimbres, which is northwest of El Paso in southern New Mexico, and we had to use it with, I think it was called Tierra Blanca outside of Hereford last spring. Hey, there's more water coming. No, our model is saying the timing is over. You've got 80 houses underwater. Give it a couple hours, you're going to start to see that water recede. We didn't give a height forecast, but we gave a timing, which was still information they didn't have in the past. This gives you a run through of the waves of water going through in 2015. As you know, it rained, what, 26 consecutive days. Someone had 4 inches of rain or more in the state of Texas. But what I want to point out, they use flow measurements. Again, this product maybe not the best use for the public because, you know, you're sitting here, you look at this bottom flow here and you're saying this purple here is 63,000 to 146,000 CFS, cubic feet per second. Yeah, what does that mean? 140,000 on the Mississippi is, okay, we have barge traffic. 140,000 on most of my Texas rivers, and you're pulling people out off of the roofs of their homes. So if you don't know the flow measurements, this product doesn't have a lot of value until a hydrologist puts it in a manner that it does add value. So the timelines and stuff, the National Water Model, again, it runs a short-term meteorology model every 18 hours. It runs an analysis of what it thinks it occurred. I said the short-term model is run every hour out 18 hours. The analysis is run every hour. Every 6 hours, they're using the American model. We're going to switch it to a model blend because blends are better than one single model. Out 10 days, and it's ran every 6 hours. And then the long-term climate model, we found there's not much use for it. But we're trying to improve our long-term climate model that's ran once a day. The goal is you put your precip inputs in. It is a different soil moisture model. It's the NOAA Landsat. So anytime you see NASA information in NASA soil moisture, that's the model that the water model is using. So we've got comparisons. We've got more data. We're going to put that into StreamFlow, and it has the ability to do its own perturbations for ensembles. We're testing out the accuracy of that as we speak. But the main thing is it allows us to start putting in a crude flood inundation mapping. Okay, so the water model, we can put in the River Forecast Center's forecast or the water model forecast and try to come up with a way of giving flood inundation. And that is something that's big. That's the big what. So what? I need water on a map so I can make a decision. I didn't think I'd see this in my career, but we got it, okay? It uses the height above nearest drainage to estimate each basin. So each basin, let's find the lowest point, call that the river channel. Then we now have elevation points from each point. So if the synthetic rating curve says 30 feet, everything that's 30 feet, we're going to call that inundation. And next thing you know, we've got a way to estimate. We tell everyone, do not let perfect be the enemy of good. The water model simulations are pretty good, okay? But they are not perfect. The high-level engineerings, if that's available, use the high-level engineering maps. But we serve the nation. It's in our name, National Weather Service. We fill in the gaps with the National Water Model so that everyone can have some form of precipitation FEM map available. We rolled it out to East Texas, the eastern 2/3 of Texas, back in September. So right now, if you went to the websites, you would be able to see flood inundation maps, the forecast from us, those that have engineering maps, and then filling in the gaps for the water model, especially over East Texas. We have the ability to show the FEMA 100-year because that seems to be what everyone clicks into. How's this compared to the 100-year flood? Oh, you're way inside the 100-year flood, or this is more than 100-year flood. So right off the bat, we can compare the FEMA maps, we can compare the Water Center maps, we can compare the River Forecast Center maps. This is one actually from from the southern Mississippi where we had a flood go through, and you can see the red hatched is a FEMA map. And it's like you're well within the boundaries of the 100-year floodplain. That gives information. We've got a flood inundation map. It's going to get out of its channels. You can see it spread out, but you don't have to worry. It's nowhere near the 100-year map. Information that's usable. We will be providing these films. We are providing these films, like I said, as of September. There are other films available. You know, the Army Corps of Engineers puts them out. There's a lot of other groups. Harris County Flood Control has their entire county ready. So which flood inundation map are you going to use? I'm going to tell you which one's the best. I tell everyone I'm a National Weather Service asset. I am not a National Weather Service cheerleader. If the FEM from us is not as good as someone else's, I'm going to tell you to go to someone else's. And I've been given the authority to do that, that my boss will try to shield me from anything from the National Weather Service. If I say, use the Army Corps map, use the Harris County flood map, it's a little bit better than ours. But if ours is the best, I'm going to brief on ours being the best. And we got to work on the vocabulary. You know, there's a difference between flood inundation mapping and flood extent mapping. One gives you depth, one doesn't. We call ours a FEM. It's not a FEM, it's a flood extent map. So, you know, how deep is the water going to get? We can only tell you the water is going to get there. We can't tell you the depth yet, but maybe in my career, we will get there. We rolled it out to these areas. as of September. So it gives you an idea what's going on. The problem is Mother Nature is undefeated. Sometimes our computing technology glitches. Mother Nature does not work on sharp right angles unless there's a levee in place. Well, this is up near Greenville. There's no levee, but we see this sharp right angle here and we say, this looks unrepresentative. This is not a totally useless map though. This is showing, you can see there's a little red triangle area here, which is moderate flooding, and it's threatening this road. We would tell everyone, everything from this highway north and west, use it. We think it's representative. But let's go back and reevaluate and submit a trouble ticket to try to fix this right angle sharp curve that's going on in this product. The heat map is what I love though. We can put in our own GIS layers and figure out when the water extent gets to the point, does it start affecting buildings? We can dive in depending on the data layer and say, is it an agricultural building? Is it a residential building, whatever? And you can start to see areas that pop. Huge areas of the river where there's no one at but cattle, that rancher wants to know, but that rancher can handle it. Let's put our resources in the areas where there's more impact. So I feel that the heat map is something better for me to get an idea so I can brief the emergency managers. The key is when you get this information, you bring into your own GIS unit and you may have a better layer. Now I want to bring up inform.us. That's the Interagency Flood Risk Management. And not only is it because there's a really handsome dude there in that third panel, me, by the way, but it's the FEMA bringing the money, USGS and the Corps bringing the technology, and the Weather Service bringing the science all together so we can create maps across. You can go right now. And if you select Water Center map, you can see all sorts of flood maps pop up based on color coding and zoom in enough, and you can see flood mapping all through the area. If it's the high level engineering, there will be flood depth. So this is the West Fork at Conroe, and you can see the base forecast of 120 feet, that we would see this much inundation and this depth across the area. If it's not covered by one of these high level engineering maps, you would see the blue lines of flood extent from our water map. So I'll tell everyone, go to the Inform site, flood decision support tool, click on Texas, and then go up to the right panel and click on turn on water model, and you will see that information. And we're using it right now to help with our briefings. But if we don't, we do have a way of clipping. So we would clip the area in general. We'd add the forecast hydrograph, and we provided this. This actually in January, we provided to the Texas Department of Criminal Justice, and that there was also a hospital unit in Dayton outside on the Liberty River. Are we going to be threatened? And we were able to provide flooding maps to say, Dayton, you're fine. You're well outside the floodplain. But the TDCJ guys, so they're like, okay, this is great. Now we want to do it for the entire state. I went, of course you do. So let's get ready to do all the prison systems around all the rivers. But this is information. I need a map. I need to know where this water is going to be. We can now provide that as of September. The problem is my son says, Dad, you give old man talks and you're an old man. And he's not wrong. I live on a laptop. If you come over here and look at my laptop right now, there's 31 Google Chrome tabs open. We do not live in a society for laptops. We live in a society for mobile. So can we make this data available? When the Bosque River flooded back in October, the emergency manager, he goes, it's me, I'm it. I have 3 things. You've got 30 seconds to get it to my phone that I can read and make a decision on. So we have to be flexible in how do we deliver that? And that's for the young'uns in the audience. That is for the new technology. I'm the science, but the technology to deliver, that has got to be where we focus on the next 5 to 10 years. The science is going to improve, but the delivery better improve along with it. So with that, more pictures of me doing my job and or vacation. That is my contact information on the bottom. So if anyone needs to ask questions, and I can't get them, but you can see I've got El Paso covered, the International Boundary Water Commission. This is the Rio Grande outside of Santa Fe. And then this is actually Toledo Bend testing a gate release. This is not in my area. This is up near Pacosa Springs, but I just said, hey, it's on the river and I'm a hydrologist. Let's take some pictures. And you can see other points across the state of Texas. I am available for questions and comments, but thank you for having me. I was so excited to be here. You can see I'm still talking fast.
Thank you very much. So if you have any questions.
Start with a softball, but also a good question. I'm just wondering, so you have this, long prolific career. You've watched a lot of things change over time. And I'm just wondering, with all of that expertise and experience, what would you say are the needs in terms of, and I'll bifurcate it, in terms of data and science. What would you say in each of those categories are really the key needs in like the 5 to 10 year time frame?
What I'm learning is my concerns for data, the skill of remote sensing has really blown me away. And I believe the remote sensing will be able to give us, I mean, think of LiDAR data 30 years ago to now LiDAR data is common. So the remote sensing aspect, if you ever ask a scientist, they're going to want more data. Give me more data. Remote sensing, gauges, radar. The kicker is I keep saying Mother Nature is undefeated. I will be honest with you. I was the primary briefer up until I had to leave to go down to the Falcon Reservoir International Workshop on Tuesday. So for Friday, Saturday, Sunday, and Monday morning, I was looking at every weather parameter I had. And I said, we're going widespread 5 to 7. I'm seeing some individual models pick up as much as 8, maybe 10 inches of rain. I think isolated totals of 8 to 10 inches of rain. I've been doing this for 24 years. We had 17 inches of rain hit. So the skill of the science, we've got to get the science advancing to capture Mother Nature. And is climate change going to be an issue with that? The phrase I use is, we know the extremes are going to get more extreme. The floods, I say this, the floods are going to get floodier, the heat is going to get heatier, and the drought is going to get droughtier. How do we account for those extremes when sometimes we can't hit the extreme in the short term? So I'm always going to say data finds its way, especially with remote sensing. We really need to focus on the science. Can you figure out the forecast sciences, the response, capturing what Mother Nature is doing? Everything is an estimate. You know, meteorology is an inexact science, and you're basing hydrology on that inexact science. We've got to find some way of capturing what is happening better. More data will help that, but it's the forecasting skill. Because we're finding with more people moving to the area, if I had to evacuate, I now need more time. So I've got to give you longer lead time, which I'm already pushing my limits, in order for you to make more decisions. So I would lean it towards, we need the science. Data is always going to be there, and people are going to get that data, and remote sensing is going to fill it. Data is important, but we really need the forecast science.
So we have a colleague here, Ashraf Rattab, who's at a meeting at the moment, but he did a study on atmospheric rivers in Texas, and the Wimberley flood was an atmospheric river. And I know it's great to see you have to use everything, but maybe it reached there faster or whatever, and then people were reporting back, and you have your models and how crowdsourcing data. You know, are you looking into atmospheric rivers much, or? You know, do you hear about it much?
It's a loaded question, because when I was in school, it was just called the Pineapple Express or the Mayan Express. We didn't call it an atmospheric river. The atmospheric river terminology really came in to the Weather Service, even though it's been in the research world for a while. The Weather Service, we finally were able to get, especially with satellite technology, finally be able to get the remote sensing outside the United States so that we could see over the Pacific, we could see over the Gulf, and we could see the boundary form. The 2016 flood event on Toledo Bend, where Toledo Bend was releasing more water than Niagara Falls 3 times over, was an atmospheric river event. We know from the Mayan Express, we know the Pineapple Express, but in the state of Texas, how it's different than the state of California, you have this huge fetch of Pacific Ocean, and you're able to see these events with more lead time. We do not see the events with more lead time here. I was trying to find out, was our Monday event an atmospheric river event, which is why the rainfall amounts forecast rain were low, because we didn't capture it. Precipitable waters could have helped out. We're looking at all the data, because the models are going to be a good job of handling 90% of the time. Partly cloudy, 30% chance, the model is going to beat the human. We've got to find the targets of opportunity. Identifying an atmospheric river is a target of opportunity. The rainfall amounts will be too low of the model. Human intervention, let's go more on the rainfall model, because we have an AR in place, and how can we add value? So there's always an opportunity for more data, and specifically atmospheric rivers, but the Gulf of Mexico being so small in geographic area compared to the Pacific, we don't get the lead time that they get.
Do you see them coming from the Atlantic through the Gulf of Mexico?
It takes a pretty unique setup. The Bermuda High has to set up in such a way, and then we get squeezed in such a way. Normally, when we're looking at that, we're focusing on the paths of any tropical storms, because they will also kind of follow the same general path. we're not seeing it in an operational sense in Texas yet. What we see is we see the pattern form from satellite, remote satellite over the Gulf. And when we see that narrowing down, we know that we're getting into that event. And then we look at the Lake Charles sounding. And when they release a balloon up, we'll be able to measure the content of water. And we know compared when it shoots off the chart, to massively moist, we've got that event going.
Yeah, and so last question, so Clint Dawson, there's a lot of storm surge, and so he was saying the National Hurricane Center has a rapid slot model and was suggesting that Corpus Christi should be evacuated during Harvey, but the ADCIRC model was suggesting not. So what happens, when you have these false positives, I mean, too much caution or too little, false negatives.
The false alarm ratio is something we have to deal with because I've been told by the #2 in the state of Texas emergency management, you fool me once, it's on me. You fool me twice, I'm not coming back to you. What we've learned though is we brief on behalf of the National Weather Service products, but we know what the ADCIRC is saying. And we tell them, this is what the Weather Service is providing to help you make your decision. But if you've got the ADCIRC, it's your decision to make, and we'll be here to help you. But this is what the Weather Service can provide. Ultimately, we have to give them everything we can and then hope that they make the decision in their best interest using all that available data. If we find out they're going to outside sources more, then that motivates us to improve our services.
So I'm going to ask you the easiest question that you're going to get today, and that is, I have so many questions to ask, but there's not enough time. So when are you heading back to Dallas?
Dallas is an East Coast city, and Fort Worth is a Western town.
So
Dallas,
when are you leaving this building?
I'm leaving this building probably around lunch, maybe a little bit after.
Okay.
Here's the deal I would say with Dallas, and it's the same with Dallas-Fort Worth. I saw a projection that in 2100, the Dallas-Fort Worth metro area will be the largest metro area in the United States. One of the primary reasons is climate, which I don't think is a primary reason. I think there'll be people leaving Dallas-Fort Worth because of the extreme climate that we'll have. But it is not bounded. Chicago is bounded to the northeast. Los Angeles is bounded to the west. New York is bounded to the east. Dallas-Fort Worth area is in the middle of the plain and has the ability to expand north, south, east, and west. Dallas has a city feel when you drive over there. Fort Worth has a western town, but there are like 9 to 10 counties as part of that, and it has everything you want. I mean, it's the 4th largest metro area right now. It'll be interesting to find out when it takes over for the 3rd. It passed Houston since I've moved there. It's passed Houston from being 5th to being 4th.
Well, I was more wondering if there's a couple minutes after your talk. I've got a phone call at 10 o'clock.
There's always a couple minutes, but the deal with Dallas, they get the humidity, they get the rain, they get a little bit of winter, and they get the flooding. So Dallas is a great forecasting challenge because also it's metro area. And when I first started, they said if it rained 2 inches in Dallas, Trinity River, Dallas is going to flood. It's more like 1.5 inches due to urbanization.
Okay, any other question? No, our time's almost done.
Yeah.
So thank you very much, Greg, today.
Right.